A, that's the typical domestic refrigerant. So that's working fluids. When you see it's a refrigerant, don't assume that's an ideal gas. Don't use PV equals RT. Don't use the entropy formula like that, what I showed you for the comments from P3, and don't use T2 over T1 equals P2 over T1 to the power K minus 1 over K. So for water and the refrigerants, what's the basic idea to determine the properties? For the working fluids with phase change, what's the basic, the basic methods? Can you I've repeated many times. For pure substances which may have phase change in the questions you have, what's the basic methods? More loudly. By knowing two independent properties, right? You must know two independent properties. With only single property, you won't be able to determine the others. Okay? Write down if you have forgotten. Okay? For working fluids, which may have phase change, maybe just write down for water and the refrigerants. Okay, in these subjects, for water and the refrigerants. By knowing two independent properties, we can find others. Two independent properties. In which case, properties are dependent. Only one case, inside the saturation region, saturation pressure and saturation temperature, they are dependent. Okay. And in this cycle, refrigeration cycle, minimum temperature is given minus 10 degrees Celsius. So we need to understand the cycle before we can interpret. So what's the temperature is for? Okay. And the maximum pressure is 1 megapascal. What's the maximum pressure? That's the condenser pressure, right? So 1 megapascal is condenser pressure, minus 10 degrees Celsius, that's the evaporator saturation temperature. Okay, saturation temperature. And then assume ideal refrigeration cycle, as shown in this figure, okay? The question is to find out specific heat transfer from the cold space. What's the cold place? And the specific heat transfer to the hot space. Okay? So one is QL, one is QH. Okay? And the coefficient of performance. If we know QH, QL, then we can calculate the coefficient of performance. Okay. Alright. So this is the diagram we haven't seen for a while. When we started the second law, the statements, they're based on two power cycles. One statement is based on engine cycle, and the other statement is based on refrigeration cycle, right? Two statements. So refrigerator is a device which transfers heat from the low temperature reservoir to the high temperature reservoir with the power supply, okay, with the energy supply. So that's the definition of the refrigerator heat pump. Okay, so that's the given conditions I already interpreted with this diagram. Because 2 to 3 is a constant pressure condensing process. Okay, so along a constant pressure. Okay, so that's the constant pressure given. Actually, there are only two pressure lines. One is condenser pressure, the other one is the evaporator pressure. Okay, so it's given the maximum pressure is 1 megapascal, and then it's given the minimum temperature, which is the temperature in the evaporating process. It's a saturation temperature, minus 10 degrees Celsius. Okay. With this given condition, it's not asked in the question, but I would like to ask you, with this minimum temperature given, can we find out the pressure in the condenser? Can we or not? Yes, because inside the saturation region, pressure and temperature, they are dependent. Okay? We don't have so many tables for the refrigerants as the tables for water. Okay? We have two tables for refrigerants. One is based on saturation temperature, the other one is the superheated vapor. Okay? So from the first table for refrigerant 134A, we can find out evaporation pressure. And with the same table, probably you wouldn't find the exact 1 megapascal, but we can find out the condenser temperature. Condenser temperature actually is lower than the temperature at state 2. Okay, because state 2 is a superheated vapor. So even you are not going to be exempt for this, but in air conditioning subjects, people are always confused by the condenser temperature and the temperature at the end of the compression process. Okay? So they are not equal. Okay? Pressure is the same because it's constant pressure process. Okay? So, and given conditions and questions. The first question, because with the application of the first law, okay, so that's in greater details than the one in your textbook, in your study guide, okay. So that's the first law applied to an open system which undertakes steady state, steady flow process with a single flow stream. So all the terms, they are in specific energy form. So you can see all the terms, the units is kilojoules per kilogram, right? Kilojoules per kilogram is not kilojoules, it's not kilowatts. Okay. And then we can ignore the kinetic energy change, potential energy change, okay? And also for any heating changes, no moving boundary. So work transfer is 0. Okay, work transfer is 0. So the energy equation is simplified like that. Okay, you already got the energy equation like that in your study guide. Okay, and that's a positive value. Okay, that's a positive value because it's a heat addition process. Okay, heat addition process. So we need to find out H1 and H4 by knowing two independent properties. We can find others. So we need other two properties which are independent. Okay, in order to find enthalpy value. And then we look at, well, I think when we are able to draw this diagram, we nearly got at least two independent properties for each of the 4 states. Otherwise, we won't be able to draw this diagram. For state 1, in a standard case, say ideal case, it's a saturated vapor. Okay, it's saturated vapor. So quantity is equal to 1, and also what's the temperature? Minus 10 degrees Celsius is given, right? So two independent properties for state 1. Okay, for state 1. That's how we can find enthalpy. And then enthalpy at state 4, we only know the saturation temperature at state 4, right? That's not enough for us to determine the enthalpy. Okay? That's not enough for us to determine the enthalpy. We need to know the quality before we can calculate the enthalpy. However, from the application of the first law, we know 3 to 4 is a constant enthalpy process, right? So if we know the enthalpy at state 3, and then we know the enthalpy at state 4. That's right? And then we have the state 3. In a standard refrigeration cycle, say we idealize the refrigeration cycle, at the end of the condensing process, it's saturated liquid. Okay? We know the quantity 0, and we know the pressure is 1 megapascal. That's right? Yes? Okay, can everyone understand this state? Because that's not only for refrigeration cycle, it's still for your final exam, for your future work. Okay? State 3, quantity is 0. And what's the other property? Independent. Pressure, 1 megapascal. Okay? So H3 equals H4. And H3, we have these two independent properties. And so the enthalpy, the properties at state 3, actually they are the property of the saturated liquid at saturation pressure, 1 megapascal. Right? Okay? So that's enthalpy, is the enthalpy of the saturated liquid at saturation pressure, 1 megapascal. Okay? From B.5.1. B.5 is the appendix for refrigerant 134A. Okay? And so QL, the first question we can answer now. Okay? So that's the H1 minus H4. Okay? H1 minus H4. That's QL. Okay? Second question is related to QH. Okay, QH. That's already interpreted from the given conditions. Okay, the given condition. The question didn't say, find the heat transfer in process 2 to 3. We need to understand in which process the heat is rejected to the surrounding. Okay, so that's the QH. Okay. We know heat rejection is a negative heat transfer process to the system. Okay, and again, that's the application of the first law to a steady state, steady flow process with the kinetic energy change, potential energy change ignored, with only single flow stream, M1, M2 equals M3. Okay, and then H3 we just found already. Okay, and H2. Okay, we haven't found H2 yet. Okay, H2 is here. How can we find H2? Okay, again, two independent properties. State 2, pressure is given 1 megapascal, and also 1 to 2 is isentropic compression process, so entropy change is 0. Do we know the entropy at state 1? Because we already got two independent properties, right? State 1. And we use these two independent properties, found H1, and also we can find entropy. Okay? So entropy is the entropy of the saturated vapor at saturation temperature minus 10. Okay, minus 10 degrees Celsius. Okay. So that's how we can find the H2. Okay. With these two independent properties, probably you won't be able to find the exact entropy value from the saturated vapor table. Probably you need to use the software. But even use the software, we understand we need to input two independent properties. Yes?
Before the exam, what would that question?
That's what I'm going to say. In the exam, you wouldn't find a very complicated interpolation. Okay, maximum will be linear interpolation between 2 points. I just can't remember exactly the questions, the solutions. But if you find very complicated, just like cross 2 pressure, saturation pressure, and cross 2 temperature, whatever, won't be so complicated. Okay, so it must be something wrong in your solution until you find.
In the exam, can we not choose like the closest value? Like, do we have to use interpolation?
If it's close, and then I will say in the question, you can approximate. Yeah, I just try to simplify. Yeah, because you are not going to be tested for something too much outside the thermodynamics. Yeah. If it's close enough, and also I've requested everyone should get a textbook. It's not my problem because the supervisors won't be me, and then supervisors always confused if you bring something else rather than textbook. So please try to get a hard copy textbook. If you can't, please come to my office. I may find not a textbook for this subject, but different thermodynamics textbook. And also, if your textbook is not the one we are using for this subject, you may have find the property tables, the scaling may be different. Okay, the scaling, even the final results will be the same. Okay, like the entropy change or entropy change. Yeah, so please notice, just note, the book you have used. You just say you are not using the Stolneck, book. Yeah, using which you just write down briefly. Yeah. No, sorry. Yeah, I've written an email. I've sent an email to everyone. Have you received that? No, you don't read. That's the problem. If I show something you don't want to see, and if I send an email you don't want to read, and if I give you some materials you just ignore, and then that's the end. Yeah. So that's important. I may send another email. Probably some people, it doesn't matter how many you send, they wouldn't read anyway. Yeah. Okay. So if you are doing the subjects, you don't read the email from the subject coordinator. I don't understand what's the point. Anyway, so that's the second question. Question asked for QH. Okay. So after we found, and then coefficient of performance actually is very straightforward after we got to QL. And from the first law, the original, I think you better listen. Okay. If you want to make some fun, or just go out. It is, as I said, from the very beginning of the semester, exploring. Yeah. I can understand if I'm sitting in the class, I may fall into sleep. Yeah. Very quickly. Yeah. But we can't be excited every day. Otherwise, no difference. Then we can't identify the excitement. So when you get the good results and then start a holiday, I think that's what we aim for. Okay. And then integration, actually, because there is only process, there is work transfer. Okay, in this cycle. So the compressor power actually is compressor work actually is the cyclic integration of the work transfer. Okay, so cyclic integration of the work transfer is equal to the cyclic integration of the work transfer. And here you may notice, QH should be negative, QL should be positive. But here we just calculate, because this is negative as well. Okay, this is negative, so that's corresponding to this one. Okay, so that's the negative work equals minus QH plus QL. Okay, and then coefficient of performance. All right, and then we are going to have a look. Before we have other two examples.